Good morning all. In this section we will see the reflection of plane wave and normal incidence. When a plane wave moves from one medium to another medium, it is partly reflected and partly transmitted. The portion of the incident wave that is reflected and transmitted depends on epsilon mu sigma of the medium. So here you can see two medium, that is medium 1 I have written as region, so region 1, region 2 and mu1, E1, beta 1, eta 1. These are the parameters associated with our first medium. Mu2, E2, eta 2, B2. These are the parameters associated with the second one. And you know, mu is permeability, it is electric field. Then beta is your propagation constant and eta is your intrinsic impedance. Okay, and this xy is your boundary and this is your z axis, and you can see y drawn in this direction. Okay, this direction. Now here I have drawn an incident wave. This one is an incident wave whose electric field I have marked as EI and magnetic field as HI. That I represents incident wave. Okay, now this is your transmitted wave in your region 2 and the subscript T represents transmitted wave. And again in region 1 you can see an arrow in the opposite direction to that of the incident wave, that which represents your reflected wave, which is marked as ER, and HR is the electric field of your reflected wave and HR the magnetic field. R represents the reflected wave. And here you can see the components. EI, that is electric field of the incident wave, is along the x direction, the magnetic field is along the y direction, and the wave is along the z direction. Similarly here also you can see the electric field of the transmitted wave is along x-axis, magnetic field along y-axis, and electromagnetic wave along z-axis. And here you can see the electric field of the reflected wave along x-axis, HR along y-axis, and electromagnetic wave along z-axis. And here it is marked as minus z because in region 1 the incident wave is moving in this direction, which is taken as plus z, and in the same medium or in the same region the reflected wave is moving in this direction, which is opposite to that of the incident wave. That's why it is taken as minus z. Okay. Now coming to the mathematical analysis, we will start from region 1. So EI, that is electric field of the incident wave, is written as EI0 into exponential e raised to minus j beta 1 z. Okay, where beta 1 is your propagation constant, z shows that the electromagnetic wave is propagating in the z direction. Now listen, here it is written as e raised to minus of j beta 1 z. So one point that you have to keep in mind is, if the electromagnetic wave is propagating along the positive z axis, then this exponential term will be minus. Okay, and if the electromagnetic wave is propagating along minus z axis, then this exponential term will be positive. Okay, please keep it in mind. Now repeat, EI is equal to EI0 into exponential minus j beta 1 z. Similarly, the magnetic field HI is given by HI0 e raised to minus j beta 1 z. Now here I have written that here EM wave is normal to the plane along the z axis, electric field is along the x-axis and magnetic field is along the y-axis. So it is clearly shown here, that is the electromagnetic wave is moving in this direction, and you can see the xy, the boundary of the two medium is xy, and that xy is perpendicular to the movement of this electromagnetic wave. So that is why it is said that electromagnetic wave is normal or perpendicular to the boundary. If this electromagnetic wave is perpendicular to the boundary, then this x and y axis along which you have your EI and HI will be parallel to this boundary. Please keep that point in mind. Here the electromagnetic wave is perpendicular to the boundary xy. So what happens is, the electric field which is along the x-axis and the magnetic field which is along the y-axis will be parallel or otherwise tangential to the xy boundary. Okay. So I repeat here, EM wave is normal to the plane along z-axis, electric field is along x-axis and magnetic field along y-axis. Then the term e raised to minus j beta z, or instead of e raised to minus j beta z, if you are using cos omega t minus beta z, then that refers to the fact that EM wave is propagating along positive z axis. And if you are writing e raised to j beta z or cos omega t plus beta z, then that means the wave is propagating along minus z axis. Okay. Now coming back to the derivation, we know E by H is equal to eta, so I can write Hi is equal to Ei by eta 1, where eta 1 is the intrinsic impedance of your first medium, and we know what is Ei. Ei is equal to Ei naught into e raised to minus j beta 1 z by eta 1, which is my equation 2. Now coming to your second medium is where you are having your transmitted EM. So that is represented by Et is equal to Et naught into e raised to minus j beta 2z. Now it is a second medium and the propagation constant of second medium is beta 2. Similarly, Ht is equal to Ht naught into e raised to minus j beta 2z. Now you know what is Ht naught in terms of Et naught. I can write Ht naught is equal to Et naught by eta 2. It's your second medium. So I can rewrite this Ht as Ht is equal to Et naught into e raised to minus j beta 2z by eta naught, which is my equation 4. Now here it is written, if z is a component perpendicular to the boundary, then the remaining two components along x and y axis will be tangential or parallel component to the boundary. Hence Hi, Ei, Ht, Et, Er, Hr are all parallel to the boundary. If we take the case of second medium also, you can see the EM wave is in this direction. That means it is perpendicular to your xy boundary. So in that case, this Et and Ht will be parallel to the boundary. Similarly, if you take the case of reflected wave, you can see the reflected wave is moving in this direction, electromagnetic wave. That means it is perpendicular to xy. Hence what happens is Er and Hr will be parallel to xy. That is written in that statement. So coming back to the derivation, we can write Hi is equal to Ht, because what is Hi? Hi and Ht are the tangential magnetic component. Okay, I told you that is Hi, Ei, here it is Hi, Ei, Ht, Et, Er and Hr are parallel to the boundary. Parallel means tangential component. So I can write Hi, which is a magnetic component of my first medium, is equal to the magnetic component of my second medium, that is Ht. Okay, this relation Hi is equal to Ht is derived under the boundary condition of magnetic field, which was given as self-study topic for you under module 2. Okay, so HI, the tangential component across the the tangential component of magnetic field across the boundary is continuous. That is why HI is equal to HT. So I can write what is HI? HI is equal to EI naught exponential e raised to minus j beta 1 Z by eta 1, and HT is equal to ET naught by eta 2 into e raised to minus j beta 2 Z, because HT is in the second medium, which is my fifth equation. Now coming to my region 1, where we have our reflected wave, I can write ER is equal to ER naught into e raised to j beta 1 Z. Here your exponential term is positive because, as I said earlier, this reflected wave is along the minus Z axis, because the incident wave is along the plus Z axis, hence the reflected wave is along the minus Z axis. That is why here the exponential term has become plus. Similarly, HR is equal to minus HR naught into e raised to j beta 1 Z. Here also the exponential term is positive because the reflected wave is along the negative direction. And now here you can see a minus sign. The minus sign is here because the direction of magnetic field of the reflected wave gets reversed with respect to the transmitted wave. Hence a negative sign is added to the magnetic field. That is, you will be having a magnetic field for your incident wave in a particular direction. Okay. This is your incident wave, and you will be having the direction of your magnetic field HI in a particular direction. Then the direction of the magnetic field of this HR will be opposite to that of HI. For example, if HI is pointing outward, HR will be pointing inward. If HI is pointing inward, HR will be pointing outward, likewise. Okay. So the direction of HI and HR will be opposite to each other. That is why here we have taken a negative sign. HR is equal to minus HR naught e raised to j beta 1 Z. But the direction of electric field remains unchanged. Okay. Now we have HR, here we have HR is equal to minus HR naught e raised to j beta 1 Z, and in terms of electric field I can write HR is equal to minus ER naught by eta 1 into e raised to j beta 1 Z, because your reflected wave is in the first medium. That is why I have taken as eta 1 and beta 1. Now at the boundary, all the tangential component will be equal, or otherwise all the tangential components will be continuous. So in medium 1 you are having two electric field tangential component, which are the EI and ER, and in medium 2 you are having one electric field tangential component, that is ET. Similarly, in medium 1 you are having two magnetic field tangential component, which is HI and HR, and in medium 2 you are having only one tangential component for the magnetic field, that is HT. So I can write HI plus HR is equal to HT, and EI plus ER is equal to ET. That is my equation 8 and 9. Now I am going to substitute 2, 4, 7, 2, 4 and 7 in my equation 9. So I can write like this: EI naught by eta 1 exponential minus j beta 1 Z minus ER naught eta 1 exponential j beta Z is equal to ET naught exponential minus j beta 2 Z by eta 2. Exponential term gets cancelled, so finally I will get EI by eta 1 minus ER by eta 1 is equal to ET by eta 2. That is my equation 10. Then I am substituting 8 in 10, so I will get EI by eta 1 minus ER by eta 1